Let's take a look at the second fundamental theorem of calculus, which kind of shows that the antiderivative and the derivative are kind of like inverses of each other, not inverse operators or whatever. They kind of undo each other. And we're going to say let f be a continuous function on a closed interval ab, and then for each x in this closed interval ab, if I take the derivative of the definite integral from a to x f of t dt, that's going to be equal to f of x. So it's kind of like I'm taking a derivative of some sort of area function, and it's going to tell me how the rate of change of the area is at a specific snapshot in time. So let's take a look at the proof. And we're going to let x be an element of this closed interval AB. And what we want to show is that this is differentiable. So we can say that f of x plus h, that's going to be the integral from a, so that'd be the integral from a to x plus h of f of t dt. So that's what that f of x plus h is. And then what we're going to subtract from it is f of x. And that's all over h. So we're just going to show that the derivative is equal to f of x. That's what we want to show. So we're just writing that down because that's where we're going. And then we'll make a note where f of x is equal to the definite integral from a to x of f of t dt. And what we'll do is I'll show you the proof for where h is positive, and then if you want to do the proof where h is negative, it's essentially the same. It's just when we end up dividing by h, we'll have to flip some inequalities. Okay. So what we're going to do is f of x plus h minus f of x all over h is, I am subtracting two integrals. And so what's happening, so anyways, what's going to happen there is, you got one that's going from a to x, and then the other one's going from a all the way to x plus h. So if I take the whole one, which is all of this, and then subtract from it the part here, I'm going to be left with the integral from x to x plus h. Okay, so what that's equal to is the integral from x to x plus h, f of t dt. And we're going to use some facts here that the function is continuous on a closed interval, and by the extreme value theorem, that tells us that the function achieves both a minimum and a maximum on that closed interval. And so what we're going to call those is little m of h and big M of h. So little m of h and big M of h. And that's just going to stand for the min and the max. And our function actually achieves those values at some particular points in this closed interval. So what we're going to use this for is that's going to bound our f of t. So little m of h is going to bound the f of t, and the big M of h is going to bound the f of t. So that means our function is just between its min and its max. Okay, and we have a preservation property of antiderivatives, or the definite integral, is if I have this property, then the antiderivative or the definite integral is going to follow that. And this is for all t in this particular closed interval. So when I take the antiderivative of all three sides, the inequality is preserved. And one thing to note is m of h, little m of h, and big M of h, they're just constants. So let's find a different color. So here we are. Um, here's our x. Here's our x plus h, and then our min is little m sub h, and it's just a constant. So when I find the area of that, I'm just finding the area of a rectangle. And the area of the rectangle is going to be the height, which is m of h, times the width. And the width is just going to be x plus h minus x, or the width is just going to be h. So the area there is going to be little m of h times h. And then we can do the same argument for the big M of h. It'll be big M of h times h. Okay. All right. So that's exactly what we just said. The area of the smaller rectangle is going to bound the area from below, and it's going to be bounded above from the big rectangle. Okay. And this is where the h positive comes into play. So we're going to divide everything by h, and because we said h was positive, we don't have to flip the inequality. If the h was negative, then we would flip all the inequalities, and the argument would be real similar. So we're going to divide all sides by h, and the stuff in the middle is going to be what our limit we were working with is going to be equal to. Oops. And so it's stuck in between two constants, little m of h and big M of h. And what we're going to do is we're going to let h go to 0, which is the we're going to let the h go to 0, which is going to let the interval get real small. And because this function is continuous, both the minimum and the maximum are going to get closer and closer together until they end up going to the same value. And that value is going to be x. So by continuity, the min and the max are going to end up becoming the same. They're going to go both go to f of x. So we have this this property right here. So we're just writing it again. Little m of h is less than or equal to the definite integral from x to x plus h f of t all over h, and that's going to be wedged between the big M of h. And since these are both going to the same place, they're squeezing that integral. It has nowhere to go. It has to go to f of x also. Thus, the limit as h goes to 0 from the positive side of this definite integral is going to be equal to f of x. Okay, and that's what our derivative was equal to. That thing right there was equal to our derivative, and so we can say that the derivative of the definite integral from a to x f of t dt is equal to f of x. So you see that when I take it's kind of like taking the derivative of an antiderivative. I'm left with where I started with. When you compose a function with its inverse, you input x, and then you do the function in its inverse, and you get an output at the very end as x. So we're going to do a couple examples of the, I think 2 examples of illustrating this. Okay. So we'll do one that's real straightforward. So let's say that we want to take the derivative of the definite integral from 1 to x of 2t plus 5 over 17t to the 4th plus 1 dt. And so essentially what's happening is the derivative is going to undo the antiderivative, and we'll be left with the original function. It's just it will be in terms of x instead of t. So real straightforward. Now if I do something a little bit crazier, let's say that our function big F of x is equal to the antiderivative from 1 to sine x of cosine squared, or cosine cubed theta d theta. So our fundamental theorem, our second fundamental theorem of calculus, said if we went from 1 to x that we had this property, not from 1 to sine to x or whatever. So we're going to have to do a little bit of substitution and use the chain rule here. And we don't really need to use the substitution. We're just going to use it to kind of demonstrate. So if we say u is the sine x, then the derivative of u is going to be cosine u. And so f of x is going to be the same thing as f of the letter u, which is the integral from 1 to u cosine cube theta d theta. Now this is what the second fundamental theorem of calculus applies to, because we're going from some constant to the variable we're in terms with, which is u. So when I do take the derivative, though, I'm going to have to use the chain rule, because it's not a function of x, it's a function of x, and we need to use that chain rule. So we take the derivative of f of the letter u, it's going to be f prime of the letter u times the derivative of the inside function. Okay, so the derivative of f evaluated at u is just going to be, by the second fundamental theorem of calculus, is cosine cubed of u, and then because of the chain rule we have the u prime there. Well, we know what u is, we know what u prime is, so this becomes cosine cubed of sine x, and then times the cosine of x. Okay, and that's usually kind of the more tricky examples of second fundamental theorem of calculus, where we're applying it, where we have this 1 to, or some constant to a function of x that's not just x. So the sine x makes it a little trickier, and we just have to remember to use the chain rule.